Okay, so thank you very much for inviting me here. I have indeed been invited to a priori to talk to you about some aspects of cosmological probes of dark matter. But as Diego just said, I'm actually originally a particle physicist, so I cannot essentially go to cosmological probe before telling you essentially to what kind of Lagrangian I want to probe. so I feel like, I'm going to try to go to first an general introduction about dark matter, about things, how we got to the point to think of we need something else than ordinary matter. I will then go to essentially a very brief, just to remind you, stuff about cosmology, Friedman, Robertson, Walker, universe. I mean, essentially repeating or maybe just reminding you some stuff that you have already heard in the first lecture. And I will just present you the standard model of particle physics just to count degrees of freedom, just for the sake of being sure we are all on the same page. And then I will go to specific production mechanism for dark matter. I will go to the freeze-out mechanism. I know it's a very well-known case. Still, I will use it again as a reference for probing dark matter, so I will go through it. And then I will go to feebly interacting massive particles, and then I will go to cosmological probes of these beasts, okay? So that's my program. So first things first, I would like to make a quick history of how we got to the conclusion that we need dark matter. And I think it's important because I still hear that some people think that we theoretical physicists are crazy about thinking that we need something extra beyond the standard model of particle physics. Do you hear me at the back? Yes. Okay, good. So, brief introduction. So we begin the story actually. Yeah, I have notes. I guess we put them onto the Slack, some link or something. Feel free to tell me all the typos you will find out, because probably there are many. And there are also many references on this, okay? So obviously about the history of dark matter, there are fantastic reviews. I will just go through some points of these reviews, okay? So there is macchina. Okay, so beyond the machina problem, so we begin with in the 90s, where people begin to essentially apply concepts of gas theory to actually particles, okay? By doing that, you get to the very frequently referred to Fritz Zwicky, okay, which in 1933 actually wrote a paper where he actually uses the virial theorem in order to essentially estimate the velocity dispersion in the coma cluster and try to compare it to the observational observations. I just want to know, is anyone ever opened the Zwicky paper? Yes? Okay. So it's very interesting because you see many things in the literature, but then when you open it, it's absolutely fantastic, just blah, 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 blah. And then one thing, suddenly blah, blah, blah. I mean, reading the paper, I realized how people were so negative about these people doing some cosmology, which was just look like cooking things. But I mean, I will tell you what I got from this paper. So essentially he uses, so we are in 1933, and he uses the virial theorem that is going to apply to the coma cluster. So we have kinetic energy, potential energy, they essentially have to come together. We have observation from Doppler shifts that tells you that the velocity dispersion in the coma cluster should be about 1020 kilometers per second. So as far as I remember, this is a number you can find in the paper. And you want to recover this from there, okay, by essentially trying to estimate what is the amount of mass as a function of the distance that it's into this cluster. Obviously, you have error bars today. This has been estimated to 1,082 kilometers per second. But this is the estimate that I have at the time. So E is going to use the total kinetic energy that is going to be 2 times the mass that is in the coma cluster times sigma v square. And is going to equate it to the potential energy. In order to do that, he assumes that this coma cluster is a sphere of constant density, okay, and radius of total mass mc. And in order to going through that, you get Newton constant times mass squared divided by r, and you have actually a 3/5 factor there, okay? So this is what you do. Then he says, very good, let's assume that in the coma cluster, we have about 800 galaxies, which have all masses of about 10 to the 9 solar masses. Okay, and then by doing that, he gets to an estimate of the coma cluster mass, which should be 800 times 10 to the 9 solar masses, which are 2 times 10 to the 33 grams, okay? Which, at the end of the day, you get 1.6 10 to the 45 grams, okay? Very good. You plug that into your equation, assuming that the radius of the coma cluster is of about 10 to the 6 light years, which is essentially 10 to the 24 centimeter. And making use of your Newtonian constant, you get, at the end of the day, that your estimate for the velocity dispersion based just on the mass that would be into what you see is 80 kilometers per second. You have a strong discrepancy between the two, meaning that you are missing something, okay? And so this is one among the first number you get from the literature where people have been estimating what amount of matter you need to have your observation that should essentially account for some mass, which is actually not completely into the luminous matter. So these are in 1933. Now, we stay with this very approximate estimation of the amount of matter we have in the coma cluster, and we get to the 1960s, where we have the discovery of the cosmic microwave background by Penzias and Wilson. And I mean, it seems completely independent, because when you usually hear very general talks about dark matter, you will hear about Zwicky and you will hear about rotational curve of galaxies. But for some reason, people never mention the CMB, but actually this is our best probe we have currently of the amount of dark matter we have in the universe. This is, okay, at the time, what they essentially see is the background level of information, okay? So actually, CMB is going to look very smooth for 30 other years, okay? So there you just have the beautiful intensity as a function of a frequency that is just a black body spectrum. So this is an important moment. Then you get to 1970s, okay? 1970s, where actually we have some papers by Ford and Rubin. Actually, there were other people before, but it's apparently the first precise measurement of rotation curves of galaxies, where they essentially look at circular velocities as a function of the distance, okay? And as you probably have already heard millions of times, you expect this, and what you have is data here. So it looks like the velocity is not, again, accounting for what you would expect. Where does this fall comes from? Essentially, so they were looking at Andromeda galaxy. So you use gravity force, okay? That should be equal to centripetal force. And you essentially, if you want them to be equal, you have an expression for your typical velocity. If you have all the mass centered into the bulge, into the visible thing of the galaxy that you see, essentially you see that this should go down with R, okay? So actually this is what you expect, okay? And thanks to spectroscopic observation, they got to the conclusion that it is flat. So again, you need some other form of matter that you cannot see, okay? And that could give rise to this flatness profile, okay? So essentially, you need not the mass all into the central part of your galaxies, and potentially with a density, actually, that has a specific dependence in the distance. Very good. Now we go to a little bit further in time, and we get to the 1980s. Apparently at the time, actually about cosmic microwave background, I learned something very recently. It's again not very relevant at the level of the physics, but did you know that originally this noise that they were hearing, they were getting into all directions in a very isotropic manner, they thought it was due to pigeon poo into the antenna? I absolutely didn't do that, didn't know that. Okay, so we have, I go back to actually CMB. And at the time, they actually were not seeing any fluctuations onto the CMB background at the level of 10 to the minus 4, okay? And this is where it became obvious that we needed, in order to explain this, an extra form of matter that does not interact with photons like the ordinary matter. In order to, clarify why, a priori, what I would need is to go to a perturbation evolution equation of matter density of matter. In this lecture, I will mainly stay at the level of background, okay? And I will tell you what should happen at the level of perturbation theory, because I will have no time to go through all the evolution equations, okay? But what I can tell you, and at the end of the day, this equation is not that much different from the one that was shown in the first lecture today. If I write matter density as some background density plus density contrast, okay, I go to Fourier, in the first part of the lecture, and I use fantastically exactly the same notation as Lam, meaning that I will also use T as proper time, eta as conformal time. I will also use prime as derivative with respect to eta, and dot as derivative with respect to time. Okay, if I use exactly these notation, I can look at the evolution of density perturbation and velocity perturbation, the two first momentum perturbation into the whatever. I take the density perturbation evolution. I take the Euler equation, the evolution of the velocity perturbation for non-relativistic matter. I combine them, okay? And I get the so-called growth equation, okay? This equation essentially goes as double derivative of perturbation with respect to time, some friction term due to Hubble expansion, and I actually get some velocity dependent of the fluid contribution here, some gravity contribution because h is related to the amount of matter you have here, and perturbation of k, okay? So these are my growth equation. You have to trust me if you never derive them. But essentially, so here we have friction. Here at the end of the day, we have a pressure term, okay? And this is related to gravity because the Hubble rate is related to what is inside. I will go back to this later in more details, but going to a universe which is dominated by matter, actually, you have a specific dependence of the scale factor in terms of time, okay? A goes as time to the power 2/3, meaning that the Hubble rate goes as 1/t, okay? You plug this into this equation and you go to specific direction. We won't go to the direction where gravity is the most important because there you have gene scale instability and growing perturbations. I'm going to go to the situation where I have actually these two terms are important. In this case, actually, you can check that there is again a growing mode as in the first lecture, and that your perturbation just scale as the scale factor into a matter-dominated era. Okay? Matter-dominated era where we expect fluctuation to be able to grow. Very good. So let's accept that, obviously. This is very sketchy. Let's accept that and see what is the importance of this quantity, okay? So if I assume you also have, if I assume that I have some, so photons and baryons, they're expected to be very well coupled up to the time of CMB, okay? Which is redshift 1000, okay? Scale factor 8 to the 10 to the minus 3, okay? If my perturbation grow, okay, like the scale factor, okay, since CMB, the only moment where perturbation in baryons could grow, okay, and that I assume that originally, okay, my perturbation are at the level of 10 to the minus 4, I cannot get to non-perturbative evolution of my perturbation. I can not get to the universe I see today, okay, with galaxies, structure, and everything, okay? So this was essentially the moment, an extra, source of, there must be definitively something else, but not at the level of a galaxies or a cluster of galaxies. at the level of at cosmological scales, okay? Good. So then we go to the 1984, 85, where they begin to do numerical simulation of structure, and they really begin to see that they can reproduce the cosmic web by introducing this dark matter, okay, that does not interact at all with light. 1992, this is 30 years after the discovery of the CMB, we see with Kobe the anisotropy perturbation into the cosmic microwave background. Essentially, they look a little bit like that, okay? So you have essentially an oscillating quantity here, okay? These oscillations, you can actually relate them to what is inside of your bath at the time of decoupling, okay? And you can only explain the features that are here if you have both baryons interacting with photons, okay, which are going to give you this effect of pressure versus gravity, which gives you the oscillation at the end of the day. And dark matter, which gives you the potential wells for the baryons to be there. By putting everything together into much details, we got to non-baryonic matter, H times H squared. So this is the ratio of the non-baryonic matter with the total density that you have. H is of the order of 0.7, okay? This is 0.12. And baryons, they are 0.022, approximatively. This is thanks to the detailed analysis of the perturbations in the temperature of the cosmic microwave background, okay? It's not by looking at rotation curves of galaxies, it's not by looking at galaxy cluster, okay? Definitively, we need much more non-baryonic matter to account for our observations. Beyond that, okay, in 2006, we got the bullet cluster, okay? There we have a situation where people have been observing two clusters that have gone through each other through three different manners. They had weak lensing, they had stellar component observation, and X-ray emitting gas, okay? By weak lensing, they could realize that there were kind of two points for the gravitational potential. They also had X-ray emitting gas that was essentially somewhere in the middle, and stellar component where you can really see like the bullet going through each other, okay? Potential wells and baryons are not at the same place, okay? And this is very difficult to explain with, for example, modified gravity. This also gives you actually a constraint on the self-interaction of dark matter, okay? If dark matter giving rise to the potential wells, okay, was as interacting as baryons, there would be not such an offset, okay? So this, and I will not discuss more self-interaction of dark matter, but essentially give you that this should be smaller than 1 centimeter square for dark matter in gram, okay? Good. So this is all for the history of dark matter. Essentially, I want everyone to remember there is that there is a long story that begins with very approximate physics that goes to a physics that I would have never time to completely cover within this lecture. And this is the one that gives us the information, okay? Good. Now, that was for the history of how we got to the conclusion that we must have something beyond baryonic matter. Now let's try to still go very approximative, but try to put some limits on the masses of what could be dark matter. Questions? By the way, I didn't ask, sorry. Please feel free to stop me at any time. But this is very story, so it's not really like probably not much question there.
So it was X-ray, weak lensing, and what was the final method of observation?
It's 3 different methods of observation. They use 3 very separated methods of observation. They put them together, and they see that essentially mass from weak lensing observation is not at the same place as X-rays. Does that answer to your question? Yes, yes, sorry. Okay, now, dark matter mass. What can we say about the dark matter mass? This is, again, very rough, but this is something you will always hear, and I'm not sure that everyone knows about where does the 10 to the minus 22 and EV comes from when you are talking about typical masses of dark matter. So I would just take, like, here again a few minutes to just tell you. So let's assume dark matter is a fermion. Okay? So with fermionic dark matter, I mean fermions in general, you cannot pack them as much as you want. Okay? There is Pauli exclusion principle. And actually, this is going to induce a lower bound for the masses of the dark matter that you can expect to put essentially into dwarf galaxies, for example. For getting this information, let me go to Fermi-Dirac distribution function. Okay, this goes as number of degrees of freedom times e to the minus e over t plus 1. Okay, this is always smaller than 1/2, let's say, if it takes g equal 1. Okay, I want to go to number density I can pack into my object. Okay, I'm going to integrate my distribution function, okay, between some momenta, okay? Considering that I can, I mean, in order to keep it into the galaxy, I can go up to escape velocities, okay? So making use of this by going to, I mean, integrating over the angle, then I just have the 0 over p max, p squared dp, okay, of 1/2, okay? Which essentially, I mean, the angles give me a 1 over 4 pi square, okay? And the integration of p squared give me a p cubed over 3 of the maximum velocity, okay? This is the number density I can have. My maximum velocity momentum is going to go as the mass times this maximum velocity escape velocity, okay? Typically, this is 100 kilometers per second. Let's go to rough, let's say rough, okay? This is 100 kilometers per second, okay? We are going to work in a c equal h bar equal 1, okay? So this is 10 to the minus 3. What is the number density into my galaxy? It's the density of the galaxy, okay, divided by mass. Okay. I want these to be always, I have put an equal, should be always smaller equal. Okay, sorry. I put them together. Typical density of a galaxy should be GV per centimeter cube. Okay. Escape velocity, I said 10 to the minus 3. You put them together. I have mass cube and 1 over mass. I have mass to the power 4. Okay, so essentially I get that the mass of the dark matter should be always, assuming GV per centimeter cube into dwarf galaxies, escape velocity of the order of 10 to the minus 3. Okay, but I have power 3 here. to the power 1/4. The overall prefactor is 30 eV, given the numbers I have taken, okay? Approximate number I have taken. So this is where the statement of dark matter, fermionic dark matter, should be always higher than few eV, okay? Everybody had seen that before? Who did not see that before? Okay, I'm happy it served, it was useful to something. It's very rough, okay? It's a very rough estimate, but gives you an idea, okay? Good. Can we go lower masses? Obviously, yes. Huh? We have bosonic dark matter. Now, there is another subtlety, which is how should I treat bosonic dark matter? As a particle or as a wave? Okay? Of a wave-like behavior, animal, whatever. So the question is again, from which moment I should consider something is behaving wave-like or particle-like, okay? Again, in order to do that, very roughly, okay, you are going to compare the Breuil wavelength of the particle to the typical interdistance of particles, okay? I just write it expressly because de Broglie is de Breuil, okay? So that when you see it written length, you know, okay? I don't know what is the origin of the guy. He was, boy, I don't know, but okay. This goes as h over momentum, okay? I said h bar equal 1. This gives me 2 pi divided by m d chi, okay? Then interdistance between particles should go as 1 over number density to the power 1/3, okay? Which is again rho divided by mass to the power minus 1/3, okay, as before. I take exactly the same number as above. Typical velocities of maximum, the escape velocity, density into the dwarf galaxies of the order of GeV per centimeter cube, imposing that the de Broglie wavelength would be smaller than the interdistance. Okay, so I should be able to consider them as particles, not something that goes continuously from one to another. I get that the mass of the dark matter should be larger or equal than something like 37 electron volt. Okay? So this is where it comes from. Then usually when you have masses below a few eV, you have something that you should treat wave-like. Okay? Okay, I don't know if you have seen that before, but at least now you know. You know why? Now, in order to know what is the lowest mass for my bosonic dark matter that hopefully is smaller than a few electron volts, okay, I have to consider this thing as a wave, okay. I still consider it's the Breuil wavelength, okay. And I ask that it's smaller or equal than the typical size of a dwarf galaxy. Dwarf galaxy. which is of the order of kiloparsec. Kiloparsec, for your information, corresponds to 1.6 10 to the 26 eV to the minus 1, okay? You use exactly the same as here. There, you plug the numbers, and you just simply get that the dark matter mass, I mean, for the numbers I have given here is 4 times 10 to the minus 23 electron volts. Typically, you will see in the literature 10 to the 22 electron volt. I mean, this is all very rough, right? But this gives you an idea. So these are old order of magnitude estimates, but I think we hear that a lot in the literature. Below EV, we have wave-like behavior. Above EV, we have particle-like fermion, blah, blah. Voila. This is essentially all these numbers are roughly estimated. I don't know if you have ever seen that before, but I think it's useful just to have an idea of what we are going to talk about. In particular, in this lecture, I will restrict myself to particle-like behavior. I think last week you had mostly, maybe or not, axion-like stuff, fuzzy dark matter stuff, maybe you were mentioned. I'm not going to consider these things, yes? What? Which thing? And then it would be what? I'm sure people did, but I cannot tell you more than that. I have to say, I have to admit that I have restricted myself to boson and fermion, but yeah, there are many things in the literature, some of better quality and less quality, I would say, but but I mean, if you have something in mind or you have a paper, I mean, we can always discuss it. But yeah, yes. To fit into the galaxy. To fit into the galaxy. Dwarf galaxies are mainly made out of dark matter. I mean, we don't see them. So you would like something else than dark matter to fit into the galaxy or something? I don't understand. Because it has to explain what is inside, right? So how do you want to explain what is inside if it doesn't fit into the galaxy? Yeah.
Maybe you're saying for free balls, I mean, all these arguments are assumed like there are no interaction. So also like Fermi Dirac.
Yeah, but I understand, but even when I know that there are other arguments one can use, I don't understand why this is an argument. Like, you can still have like dark matter with this kind of wavelength, just a certain density of fire that you can compute and the speed before. Now I know there are other arguments that say that this kind of mass will not work, but this is not one. But all that I don't understand why this should.
Okay. Okay, but maybe we can talk later. I'm not sure. Okay. So, starting with this assumption, I mean, again, very rough, but keeping in mind that I will stay with masses above electron volt, I will tell you some further, I mean, assumption that we usually make about dark matter. Typically, the properties that we have, I mean, what we expect from dark matter is that it cannot be a standard model particle. This is, I mean, among other things, why I will go very quickly into a standard model. And actually, another thing I would like to do into this lecture is to go back to the situation where we could have dark matter in the form of a neutrino, the left-handed neutrino. We all know that it's not possible. I mean, we have, I mean, as we will see, there are good arguments for that. But I find it's a very nice example of a weakly interacting massive particle. So we just use it as an example, okay? And essentially show you why it doesn't work. The second is that the dark matter is neutral, meaning that its electromagnetic charge is equal to 0, okay? Obviously, you have many symmetries, among other things, into the standard model. Dark matter can certainly have charge under the SU2 gauge group, for example. Finally, also, I mean, you can also, I mean, there have been arguments for potentially having a dark matter that could be mealy charged, but all the dark matter cannot be mealy charged. You have constraint on that. So I will assume that dark matter is electrically neutral. Finally, dark matter should be stable and massive. By stable, I mean that its lifetime should be much larger than the lifetime of our universe. And massive, essentially, to allow for a bottom-up structure formation. So these are the main ingredients I will use, together with the fact that I will work with a particle dark matter, which is a mass larger than a few electron volts. Okay. Okay. Now, quick reminder about cosmology tool. You have the metric. I will use the same with the same notation. So this is very useful. As the previous lecture, C, I will take it to 1. A is my scale factor. DL is my line element squared, which can have different expressions, especially if you would consider non-flat universe. I mean, you can go into the details of that. Essentially, I will stay at the background level, and I will use the fact that cosmic microwave background tells us that our universe is rather flat, okay? So, as I think was done in the previous lecture, I will essentially assume I have a delta here. I have my scale, my conformal time that I relate to the proper time, as in the previous lecture. I have the Hubble rate. okay, which is 1 over A dA over dt. The Hubble rate today, we usually write it as 100 times h kilometer per second per megaparsec. Okay, with this h equals 0.7 order. Okay, to be more precise, this is from CMB Planck observation. So this is small h and this is h naught for notations. And we have also the redshift that just, scale factor goes as 1 over the redshift for large enough redshifts. Assuming that we are going to work with perfect fluid in a homogeneous anisotropic, at a homogeneous anisotropic level, I can describe my fluid with pressure and density, and I will relate it one to each other with the equation of states, okay? Typically, you can use the stress energy tensor that takes the form minus rho p, p, p with zeros, if you consider perfect fluids. And you have pressure that is related to equation of states through the, pressure related to density through the equation of state which is equal to 0 for matter, which is going to be 1/3 for radiation and -1 for, say, a cosmological constant. I can look at conservation of energy. I think, as was said in the previous lecture, in an expanding universe, we are going to have extra input from the scale factor dependency in time, okay? In order to do it in the right way, you should look at the covariant derivative of the stress energy tensor. That should be equal to 0, okay? And when you look at covariant derivative beyond Minkowski space, you have the introduction of the Christoffel symbols. These are going to be different from 0 into, in our case. Essentially, these guys are derivative of the metric with respect to the coordinate, okay? So I can write the full expression. Here, our metric had the dependency in time. You are going to have derivative of the scale factor, meaning that you are going to have the scale factor, Hubble rate that is going to pop up into your conservation equation, okay? If you have never done, please compute the Christoffel symbols. But at the end of the day, this gives you, at the background level, this conservation equation that you probably all know very well, right? I'm missing something? This is a mu? Mu? Which one? There? Mu nu, mu mu, alpha alpha nu, yeah. What happened? No, no. It's okay, no? No, no, it's, I mean, this is a mu. So here, essentially, the only true indice is nu. Where are you? Okay? So it's only the only indices I should have left is nu. Okay? I have only nu left, it's sum over mu. Here it's sum over mu, sum over alpha, I have only nu left, right? Here it's summed over mu, summed over alpha, I have only nu left. Now I could make it up and down or something, but it seems to be okay with my notes at least. Okay? Is that okay? Yeah. Okay. Sorry if it's not very clear. My mu and my nu are sometimes very similar. I'm really sorry for that. Okay. From this, going back to the expression of this equation of states, we directly see that depending on the equation of states, we are going to have different dependency of the energy density with the scale factor that is hidden into my h, okay? In particular, dark matter density scales as a to the minus 3, okay? Radiation density scales as a to the minus 4, okay? And cosmological constant is just a constant, okay? But you can come back plugging into the equation of states and you will find out these results, right? Okay, this is for evolution. This is obviously things I'm going to use. Now, if I go to, I would like to also know the relationship with between the Hubble rate and each of the components of the universe. For that, I should go to Einstein equations, okay? Einstein equations that relate the Einstein tensor, actually, which is related to the geometry of our universe, to what is inside our universe, which is the stress energy tensor. These can contain, I mean, rho can be a sum of different components. This is essentially some extra derivative of the Christoffel symbols, so double derivative of the metric, okay? You can expect that what you are going to get from this equation is a dot dot or h square equations, okay? These are what we call the Einstein equations. If you never played this game, please go ahead. The expression of the Einstein tensor in terms of the Ricci tensor and so on are in my notes. Please go ahead, but you will get 2h squared, okay, equal the Hubble scales today times the sum of the different components, a to the minus 3 times 1 plus equation of state of each of these things, okay? You also have that a dot dot over a so essentially the acceleration also depends on what you have in your universe, but in particular depend on the equation of states. Okay, what you see here is that in order to have, this is a minus sign, but we observe an accelerated expansion. Okay, to see this positive, you need at least one field that is going to dominate and that is going to have an equation of state larger than minus 1/3. okay? Which is not -1, by the way. So again, sorry, these omegas, so I said before getting to the details, but these are densities divided by the critical density, okay, where the critical density is nothing but 3h squared over 8 pi j, the Newtonian constant. That come from here. Sorry. For the different component, I mean, it happens that cosmological constant, if you take a lambda CDM universe, cosmological constant gives that this quantity omega lambda naught should be of the order of 70%, okay? Dark matter plus baryons are the other 30% today, okay? Essentially, dark matter account for 25%, baryon only 5%, okay? So there will be about 5 times more dark matter than baryons according to CMB. From these equations, I can get, assuming that there is one single fluid that is dominating the universe, say matter or radiation, which will happen in previous times, okay? I can essentially extract dA over dt as a function of the things that are inside. In a matter-dominated era, where the fluid dominating the history of the universe is going to have an equation of state equal to 0, I have that the scale factor is going to scale to t to the power 2/3. In a radiation-dominated era, I have the scale factor that is going to scale as 1/2. Yes. Sorry? Rho critical, this is general at any time. But if you want to have rho critical today, okay, it's H naught. I'm sorry if this is a little bit boring for those who already did that, but it just reminds very general things. From this, I get the scale, the Hubble rate, okay? And I see that in any of these cases, the Hubble rate is essentially going as 1 over the time, the proper time, okay? These are all things that we are going to use in the next lecture, so I just prefer to keep them there. Another thing that we are going to see is that essentially when the universe is dominated by radiation, okay, so H squared is going to go as rho radiation, okay? The radiation is going to be just simply depending on the only quantity that we can have, which is this temperature, okay? Rho is dimension 4 in mass, so rho goes as temperature to the 4 power, okay? But H goes as 1 over time. So we can, in a radiation-dominated era, for example, relate temperature. Rho goes as T temperature to the power 4. There, H goes as 1 over T, okay? So essentially, we see that temperature should scale as time to the power minus 1/2. And if you want to have some numbers, say temperature of the order of MeV corresponds to time of order of 1 second. if I have a prefactor, which is the number of relativistic degrees of freedom at that time to the power minus 1/4. Okay, this is valid only in radiation dominated era, but this gives you a rough estimate of temperature versus time relation. Okay. And in order to have a more precise one, I have copied into my lecture notes the Fermilab history of the universe scale, which is something that was appearing in the Kolben-Turner thing, but this is something I always go back to if I want to have an order of magnitude estimate of how to relate scale factor to times to temperature very fast, very quickly. I always find it useful. Any further questions here?
I have one, but it's about something that you said.
Yeah.
For you an estimation, an estimate of the dark matter bands, by assuming that it's made up of free fermions, right?
Mm-hmm.
Is this likely to be true?
Sorry?
Is it likely to be true that I know it was a relatively still, but is it likely to be true?
You mean that fermions that do not have any interactions? This is what you don't like?
No.
Ah.
The fact, I get it that it was just an estimate.
Yeah.
But is it realistic to assume that dark matter is made up of non-reflective particles? This is my question.
Essentially all, I mean, sorry, except this is what simulation usually do. I mean, it's only big bubbles that do not have any other interaction than gravitational interaction. Does this answer your question?
Can you please repeat that?
So you are asking me if it makes sense to consider dark matter as something that just interacts with gravity. This is your question?
Well,
no. Okay, so then I don't.
Well, you use the Fermi statistic, right?
Yeah.
This means that fermions that made up dark matter have no interaction at all, right? Because fermi
It's for free fermions. With chemical potential equal to 0, yeah? Chemical potential equal to 0. Mm-hmm. Yeah. I mean, I'm not sure I see the question. Maybe there is something more profound that I don't get. But I mean, if you are asking me if we can have dark matter without like any interaction, and that would be like free, maybe thermally, that have their own thermal distribution. That's your question, maybe. Okay. You mean that you would like to have something that behaves differently potentially with a different distribution, because if not, you don't know how it is produced. This is your problem? Okay. Maybe you can, yeah. I don't know up to which point it would modify. I mean, this is a very rough estimate, I have to admit. But no, I see your point. Yeah. Now, yeah, you can always imagine that dark matter has been produced through a non-thermal, through a process that would give rise to distribution that would be similar to the Fermi-Dirac one, even though they are non-thermally produced. So possible. Yeah, I see your point. Yeah, I have. Yeah, sorry. Yeah. It's Maxwell-Boltzmann, yeah. Yeah, I agree. Mm-hmm. Thank you. Yeah, yeah. Okay, other questions? No? Good. So, again, quick reminder, and sorry if you are all very much knowing all of this, but I would just like to count the number of degrees of freedom we have in the standard model. So, I said the dark matter cannot be standard model-like. Cannot be a dark matter particle that is from the standard model, and it could be electromagnetically neutral, okay? Now, in all my calculation, I will have to know a little bit of what are the number of relativistic degrees of freedom that are available in our universe, at the very least, into the standard model of particle physics, okay? So let me just put them as they are into, say, doublets of the standard model of SU2, okay? We have the left-handed leptonic field that contains neutrino left and lepton left. We have the lepton right, okay? We have the quarks, U left and D left, quark right and D right, okay, that I don't put into doublets because for me the standard model is SU2 left. I have not enough space. I have the Higgs that a priori before symmetry breaking I should put all the scalars into it. I have gauge bosons. This would be the U1 hypercharge gauge boson. These would be the SU2 gauge bosons. And I have the gluons. Okay. Now, what are the number of degrees of freedom I would typically give to these guys? Let me begin with the bottom. So gluons. Actually, I should count all photons. Let me begin with, so these guys, after symmetry breaking, they are going to absorb the scalars into the Higgs, okay? And they are going to give rise to photons, Z and W plus W minus, okay? Photons, two polarization, number of degrees of freedom are 2. Here, 2 degrees of freedom for polarization plus mass, okay? I have 3. Okay, quarks, I have 2 spins, I have particle, antiparticle, and I have 3 colors. Three times 2 times 2 times the number of families. I have 3. Leptons, leptons left and lepton right. So here I have put U right and U left together. Again, I have 2 spins times 2. Okay? No colors. Neutrinos, I'm going to consider 2 degrees of freedom. If there would be Majorana, it's very clear. If there would be neutrino left and neutrino right, essentially to the standard model BAF, only the neutrino left are going to contribute, so still number of neutrinos equal 2. Okay, in the estimates I will consider. Gluons, I have again 2 polarization and 8 of them. And I'm left with the Higgs, okay, which is 1. You sum them all these degrees of freedom, and you get to approximately 100 degrees of freedom, 106.75 into the standard model, okay? This is something I'm going to use later on a little bit more. Now, as I said, within the standard model, we have, going through all of them, either they are charged, okay, or they interact too strongly with the other particles, okay, they are light, or we have the neutrino left, okay, the neutrino left that is not charged and that interact weakly with the standard model, which could be our first potential candidate for dark matter. We all know that is not the case, okay? But as I said, I will use it as a benchmark for a WIMP, essentially, okay? In the standard model of particle physics, essentially this guy is going to get his interaction with the rest of the standard model through its kinetic term, okay? Its kinetic term that includes the interaction with the gauge bosons, okay? And from these, I essentially get interaction between Z boson and standard model fermions, or depending on the family, with the lepton through W exchange. Okay? Each time I have two weak coupling entering into the game. Okay? So very rough estimate. Of the typical cross sections that are coming into here, okay? If the neutrino mass, and please be very, so this is going back to where we didn't know anything about the mass of the neutrino, but assuming that the neutrino mass could be larger than, say, the temperature and the mass of the W's or the Z's that are here, okay, which is obviously not true, okay? We would essentially have the annihilation cross-section of neutrinos into fermions, for example, of the standard model, that would be expected to scale as J squared, and then I need a mass squared to get to a cross-section, okay, which would be J squared over M squared. Okay, this is the typical cross-section that you expect for a WIMP, okay? Neutrinos are just a WIMP. We just know its mass, but essentially this is a WIMP, okay? Now, what did I, yeah. Now, if I'm considering situation where the temperature of the universe is much larger than the mass of the neutrino, then temperature is going to play the leading role, okay? Yet I still have, sorry, I have put J squared, but I have J squared, which is J to the fourth, okay? You agree with me, I guess. So here, I still expect to have these W's to pop up, okay? These are in the propagator, so I expect 1 over m to the square, okay? Times square again. So I expect this dependency, and to make dimension right, I need a temperature. Which is not correct. Yeah. But no, sorry. What's wrong? Should be t to the 5. What did I do? I cannot think anymore, sorry. What did you say? Yeah. So it's n times t squared, yeah. Sorry. Yeah. Okay. Now, beyond the standard model, I'm going to consider a very simplistic extension of the standard model. I'm just going to assume that I have a single extra field beyond the standard model, which is going to be a fermion, and a mediator of interaction, which I'm going to consider that is a scalar, okay, beyond the standard model. So my Lagrangian is, so I mean, on very general ground, I can assume whatever it is actually as a beyond the standard model extension. I could add the scalars, I could add fermions, I could have just a scalar that interacts with the standard model, give rise to the relic abundance. Here we just add a standard model fermion, a bath particle, and I will couple it to some standard model particles, and I will consider a Yukawa-like interaction. In that kind of situation, whatever is chi, scalar or fermion, in order to have my candidate to be stable, I would have to assume some symmetry that will prevent my dark matter to decay into the standard model, okay? This is going to be a Z2 symmetry, okay? Under the Z2 symmetry, my dark matter and my bath particle are going to go to -1. My standard model field is going to be even under the Z2 symmetry, meaning that I cannot have my dark matter decays into directly standard model fields. This is what I'm going to assume here. I have many possibilities. I could have my dark matter that is spin 0, my dark matter that then this guy, depending if it's a lepton, it's a scalar, it's a boson. I mean, I will have to adapt. I will, as I said, consider that this guy is a Majorana fermion. And that this guy is a scalar, okay? In that way, I can connect it to some standard model fermion. That could be a lepton or that could be a quark. From the moment I assume that this guy is a lepton, I'm going to need to have an electromagnetic charge for this B particle. From the moment I assume that this guy is a quark, I'm going to need to have colored properties for my B field, okay? These will be the annihilation processes that could give rise to my relic abundance through B exchanged. But now that my dark matter is not anymore gauged under SU2 symmetry, I will consider that this has electromagnetic charge equal to 0, and I will also assume that it has no SU2 charge, not any, okay? So it's a singlet under SU2. I will consider the possibility to have this coupling to be very small, very suppressed. In the latter case, I could have my B field that could be actually interacting with the standard model particle in the early universe and decay into dark matter and storm standard model field and give rise to all the relic abundance of dark matter. By considering this situation, I get to the multiple possibilities of production of dark matter that I would like to discuss into these lectures. Here is the relic abundance. Say that this is the relic abundance I want to have to account for all the dark matter of the universe, okay? Within the context of this kind of scenario, where say this is a Majorana field and this is some bath particle that could be charged under SU2 or SU2 cross SU3, depending on the value of the coupling, I would have different dependency of the relic abundance as a function of the coupling. For the largest value of the coupling, say larger than 0.1, I have the typical, I'm going to have a typical WIM behavior. And as we will see, this will go actually give rise to a dependency of omega that decreases for increasing value of the coupling. Because I have a bath particle in the story, I could have the relic abundance of dark matter, not especially due to this production mechanism, but actually due also to take into account the annihilation processes of the bath particle and the co-annihilation processes of the bath particle together with my dark matter. In the latter case, it could be that the relic abundance of the dark matter is going to be completely dependent only on, at the end of the day, the properties of the bath particle in the co-annihilation situation. In the latter case, I will have a relic abundance that will not depend actually on the dark matter coupling for lowering the value of the coupling. My whole goal is to explain you that in much more details tomorrow. Then, actually, my coupling is going to be so small that I'm not going to be able anymore to allow for chemical and kinetic equilibrium in my plasma. This is something another point I will get to. So this is WIMP-like. This is co-annihilation. And I will enter into a situation where actually my relic abundance is going to depend again on the value of the coupling. This is what is called conversion-driven freeze-out. Going to even lower coupling, I'm going to have yet a different dependency in coupling, which actually is going to be what is called freezing. Here, my dark matter is going to be completely decoupled, both kinetically and chemically. And finally, going to even lower coupling of the dark matter, I would just get a dark matter density that will, again, not depend at all of the coupling. This is what we call super WIMP. My whole point tomorrow is to go through the details of all these mechanisms. So I was told about 1 hour and a half, which I think I got there. What I had also prepared is a little quiz, just for the fun, just to make it a little bit. So if you are interested, I mean, the one of today is very boring. I mean, let's put it just for the fun. Let's see if you are interested or not. So if you go, everybody is connected to Slack, I guess. So here is the Slack. The link is on Slack for lectures on week 2. You can all connect. It's 3 very stupid questions. I mean, 3 very general questions. And the idea is to, I guess, everybody is going to get them, and there is nothing to discuss. I'm also discovering the tool, so I hope, did you get it? It's not working, the link? Ah. I hope that the answers are going to appear here. I have no clue. It's also a question of reading the statement up to the end of the sentence. I mean, which is another exercise that you are trained a priori at university. You can have multiple answers, huh? You can have multiple answers. There is no most correct. You can have multiple correct answers. Sorry, I didn't mention. Yeah, actually, I should not show you the answers appearing. So how many are we? You have an idea? How many are we in the... So I have 13 answers. I don't know if I begin to comment, or are there still people feeling the thing or not? 5 minutes? I'm very surprised by the answers. I guess it's not reading the questions. I have 24 answers. Yeah, but with 30% people telling me that it's 70% of the matter energy content, which is maybe because they didn't read, or like it's the way I should have put matter slash energy or something. So you learn to read the entire question up until the end. You what? Should go. Okay. Okay, so let me project the answers. Okay. So I don't know if you're still feeling, but so I think that most of the problem is reading the question up until the end. So we know that dark matter represents 70% of the matter energy content of the universe. So probably I was not clear enough about what is omega. Omega essentially tells you the amount of the part of each pieces into the matter energy content of the universe. And essentially, it's a cosmological constant that would be 70% of the matter energy content of the universe. Now, dark matter represents about 85% of the matter content of the universe. So if this is what you had into your head, it's absolutely correct. But yeah, I'm just surprised by the answers. So it's 5 times more prevalent than ordinary matter according to rotation curves of galaxies. Obviously, there I wanted to insist that it's not rotation curves of galaxies that tell us this information, but it is CMB, which 43% of the room got. I'm very surprised. I was expecting 100%. So maybe the questions are not so stupid after all. I cannot know your name. I cannot know anything about you. So it's not completely useless. So dark matter should be neutral under SU2 left. This is not true, actually. Dark matter can have quantum number under SU2 left. So you have these minimal dark matter scenarios that are actually still completely viable. Dark matter candidates, which are extremely minimal. So dark matter could be whatever into whatever representation of SU2, okay? Doublet, triplet, single, I mean, depending on its scalar or fermion, but it's possible, actually. It should be a fermion, its mass is larger than a few eV, so there I wanted to insist that, no, I mean, it can be a scalar, okay? So If you have any question of what I'm saying now, compared to what is written here, please just, it's the moment, ask. um, so, dark matter mass shall be larger than 10 to the minus 22 electron volt for fermionic particle. I mean, at the end of the day, it's true, right? I mean, it should be larger than 10 to the minus 22, but it should certainly be larger than electron volts, which 59% of the room got. So for the galaxy, it was actually 10 to the minus 22 electron volts. Then considering Friedman, Roberts, Walker, a matter dominated the universe scales as a to the minus 3. So it's wrong because Hubble rate is h squared. It goes as rho, so a to the minus 3 half. So it was just to insist on the h squared, which you always forget, and then you get everything wrong. So an equation of state smaller than -1 is necessary condition for accelerated expansion is -1/3. I mean, this has nothing to do with dark matter, but I always find nice to know about it. The Hubble rate scales as 1 over temperature in matter-dominated era, and I think I had 1/t² also as a proposition somewhere, yeah. So actually, it's always 1/t in radiation-dominated era, matter-dominated era. It's always useful to have order of magnitude estimate, so keep it in mind. And then bath temperature scales as t to the -1/2. I think it was still on the blackboard. So yeah, it's true. So I'm very surprised about your answers. I guess you didn't read correctly. Who found this absolutely irrelevant, this quiz? Who wants me to make quiz for the next course? Nobody. Okay. So you don't want quiz? Okay. So I mean, I personally do it with my students because I mean, you'd say you have a lot of information during a lecture, and actually there is only a few things you should remember. And I think the few things I try to emphasize them into these questions, which are very, I mean, small things actually. Okay, so so you are not forced to try the quiz, and I cannot know who you are, so I think it's always just useful just for yourself. But then you think whatever you want. Thank you.